So in last video we discussed about the occurrence and extraction of lanthanides, and lanthanides are extracted from the monazite mineral, and at the time of extraction two important steps are there. One is concentration of mineral and other is cracking of mineral or processing. Now next step is individual separation of lanthanides. Now due to same charge and almost same size, similar chemical properties, it is difficult to separate one lanthanide from the other. And methods like fractional crystallization, fractional precipitation and fractional thermal decomposition have been developed for the separation of lanthanides, but these methods have very tedious and they are very slow. But recently, by considering basicity differences of lanthanides, these are separated by ion exchange methods and solvent extraction methods. Now first of all, we are going to discuss the ion exchange method for the separation of lanthanides. It is the most rapid and effective method for the separation and purification of lanthanides. It involves the adsorption of lanthanide ions on cation exchanger resin followed by preferential elution. It means when a solution containing lanthanide ions, it is passed through cation exchanger resin. So these lanthanide ions, these are exchanged with protons of the cation exchanger resin, and there is a formation of bands on the surface of, because of adsorption of these ions, there is a lanthanide ions, there is a formation of various bands on the surface of cation exchanger resin, and the rate of lanthanide ions exchange with the H+ ions of resin, it is directly proportional to concentration of lanthanide ions in the solution and charge on the ions, whereas the rate of adsorption or exchange, it is inversely proportional to the size of hydrated ions. But we know that for equimolar solution, the charge carried by lanthanides, it will be the same, that is tripositive. All the lanthanide ions are tripositive, so charge remains constant, and if the concentration is same, that is equimolar solution if there, then the rate of exchange, it will be solely governed by the size of hydrated ions, and size of hydrated ions depends upon the atomic size or ionic size of the species. And you know, because of lanthanide contraction, the ionic size decreases from lanthanum +3 to lutetium +3, and as the size of lanthanides decreases from lanthanum to lutetium, size of hydrated ions increases. So from lanthanum +3 to lutetium +3, size of hydrated ions increases. This is very important. So greater the size of hydrated ion, lesser is the rate of exchange. It means from lanthanum +2 to lutetium +3, as size of hydrated ions increases, the lutetium ion being a larger hydrated ion, it has a lesser rate of exchange, whereas lanthanum ion, lanthanum +3 hydrated lanthanum ion being a smaller size, it has a greater rate of exchange. So size of hydrated ion increases from lanthanum +3 to lutetium +3. So lutetium +3, it has a larger size, and lanthanum +3, hydrated lanthanum +3 has a smaller size. Now, as I said, when the solution containing lanthanide ions, it is passed through cation exchanger resin, then slowly there is a formation of bands. So first step is exchange of lanthanum ions with H plus ions of resin. So as soon as this solution is passed through resin, cation exchanger resin, so there is an exchange of ions, lanthanum ions with H plus ions, and the smaller hydrated lanthanum ion La plus 3 exchanged first, actually lanthanum plus 3 exchanged first and bound to the resin more firmly, whereas larger hydrated lutetium ion exchanged at the last and less firmly bound to the resin. As already I told you, the exchange capacity depends upon size of hydrated ion. Size of hydrated lutetium ion is big, and therefore it will exchange at the last. It has slow rate of exchange. And size of hydrated lanthanum plus 3, it is small. It has greater ability to exchange with H plus ions of resin, and therefore it will be exchanged first and bound firmly with the resin. Thus, the lanthanum plus 3 ions get adsorbed on the surface of resin in the form of bands depending upon the capacity to exchange with H plus ions of the resin. So accordingly there is a formation of different bands. So in the beginning, as soon as this solution is poured, so mixture of lanthanum ion solution is poured on the surface of resin, so immediately there is a formation of band of lanthanum plus 3 ion, because it has smaller size of hydrated ion. It has a greater tendency of exchange, and first band will be the lanthanum. Then next band will be for cerium plus 3 if there. So accordingly there is a formation of various bands, and at the end, being a larger hydrated size, lutetium plus 3 has a less tendency of exchange, and therefore its band will be at the end, or last band will be for lutetium plus 3. And this is the exchange equilibrium. Ln plus 3, lutetium plus aqueous solution of lutetium plus 3, when comes in contact with resin, HRS, S stands for solid. So H, this is the exchangeable proton. Then Ln plus 3 exchange with this proton, and there is a formation of LnR3. So this is the adsorbed lanthanum ions on the surface of solid resin, and H plus ions get free, or they will be exchanged with the lanthanum plus 3 ions. Now next step is elution. Elution means the preferential separation of lanthanum plus 3 ion bands by adding suitable eluent is called elution. Eluent is weak acidic solution containing complexing agents like ethylene diamine tetraacetic acid, citric acid, and ammonium citrate. For example, these are the various bands, and when the solution containing weak acid and complexing agent, it is passed through this column, then actually the mixture of eluent, or eluent is a citric acid plus ammonium citrate. So when it is passed through this column, there is a elution of these ions, and elution means what? The preferential separation of lanthanum plus 3 ion bands by adding suitable eluent. It is called as elution. Now complexing agent enhances the rate of elution, and during the elution process, lanthanum plus 3 ion bands slowly moves down, and hence lutetium plus 3 ion band is eluted first. Actually, at the time of elution, the adsorbed lanthanum ions involves stepwise removal of lanthanum ions from the resin in the form of complex species. So slowly elution process will occur and lanthanum plus 3 ions band slowly move down, and hence lutetium ion band is eluted first. Actually, this lutetium plus 3 ions, these are loosely bound with the resin and therefore they are eluted first. This band slowly goes down and it will be taken out as a different fractions. So first fraction, second, third. So after completion of this band, first band, second band will be eluted. So in this way, step by step, that is lutetium plus 3 is released by ytterbium plus 3, then ytterbium plus 3 it will be released by thulium plus 3, and so on, and at the end there is a elution of lanthanum plus 3. So elution of lanthanum plus 3 ions involves stepwise removal of lanthanum plus 3 ions from the resin in the form of complex species, followed by readsorption of released lanthanum ions from the complex species further down the column. Now stability of lanthanum plus 3 complexes increases from lanthanum plus 3 to lutetium plus 3. Stability of lanthanide plus 3 complexes increases from lanthanum plus 3 to lutetium plus 3. Actually, stability of coordination complex depends upon size of cation. Smaller the size, greater is the stability. Okay, so lutetium plus 3 has a smaller ionic size because of lanthanide contraction, and its complex will be stable, and therefore complexing ion or eluent when reaches to the lutetium plus 3 band, then it has a greater ability to form complex, and therefore it will be eluted first. So as soon as lutetium band is over, then ytterbium band will be eluted, and so on. So lanthanum ions which form less stable complex tend to exchange position with those with lanthanum ions on the resin which form more stable complex. Meaning of this is lutetium plus 3 released by ytterbium plus 3, because ytterbium plus 3 has a less tendency to form complex, and therefore lutetium plus 3 is released by ytterbium plus 3, which is in turn released by thulium plus 3. Thulium plus 3 has less tendency to form complex, and therefore ytterbium it will be released by thulium plus 3. And this is the exchange equilibrium. So at the time of elution, so as lanthanum plus 3 ions adsorbed on the surface of resin in the form of LnR3, NH4 plus from the eluent when comes in contact with this adsorbed lanthanum ion, then it replaces lanthanum ion and NH4 plus gets adsorbed, and lanthanum ion it will be free. As soon as lanthanum ion sets free, it combines with citrate ion, which is a chelating ligand, and there is a formation of lanthanum citrate complex, and this lanthanum citrate complex comes down and it will be separated as a separate fraction. So in this way, complexing agent plays important role. It increases the rate of elution by forming the coordination complex with lanthanum ions.